A single memory die sits on the table, a YMTC 270 layer 3D NAND chip pulled from a commercial solid-state drive, small enough to rest on a fingernail, carrying inside it a structural decision that its black epoxy shell conceals entirely. We are going to take this chip apart layer by layer, from that outer package down to the molecular bond at its center, and the deepest layer is not a materials breakthrough or a process node. It is an architectural choice that was shaped visibly and legibly by the walls built around the company that designed it. The package comes off first, then we count what is stacked inside, then we separate the die into its two constituent wafers, and then we look at the seam between them, because the seam is where this chip does something the dominant approach in the industry does not. The cuts run in order: outer shell, then the vertical stack inside it, then the two-wafer split, then the logic wafer and its process, then the bonding interface, and finally the architectural logic that connects all of it to the competitive environment that produced it. The chip arrives in a package that gives nothing away: black epoxy overmold on the top surface, a conventional pad array on the underside, and nothing on the exterior that would distinguish this die from a Micron or Samsung part in the same form factor. Commercial teardown reports confirm the package is industry standard, and that standardization is not incidental. It is a design requirement. YMTC's commercial ambition required that storage controllers, solid-state drive firmware, and host systems treat this chip as a generic NAND device. A proprietary package format would have demanded custom firmware support and controller validation from every potential customer, which would have closed most market doors before the first shipment. The exterior conceals the architecture completely, and that concealment was a precondition for market entry, not an afterthought. Removing the epoxy shell reveals the die, and the die, under magnification, immediately shows that the layer count is real. The vertical stack is physically visible as a dense, stratified cross-section when the chip is cleaved for analysis. The 270 layers are not a marketing number applied to a conventional structure. The structure is genuinely vertical, and counting those layers is the first interior cut. Industry teardown analysis and YMTC's own production announcements describe 270 vertical layers of memory cells in this generation. Earlier generations from the same company shipped at 128 layers and then at 160 layers. The current generation represents the mass production peak as of the company's public statements through the 2023 and 2024 window. No independent benchmark has confirmed read and write performance at full commercial scale against the published specifications, and that distinction matters when evaluating what the layer count actually delivers to an end user. The drive to stack memory cells vertically is an industry-wide response to a physical boundary. As planar NAND shrank cells horizontally toward the lower limit of cell-to-cell isolation, every major producer pivoted to building vertically instead. Samsung, Micron, SK Hynix, Kioxia, all of them rebuilt their NAND manufacturing around vertical stacking because horizontal shrinking had run out of usable road. YMTC entered three-dimensional NAND later than those incumbents, which meant it did not carry the legacy investment in a particular monolithic stacking process recipe. That late entry position is the first structural condition that shapes what appears at the next layer down, because a company without a sunk cost in one approach is more free to try a different one. The layer count alone, however, does not explain the architecture. Samsung's three-dimensional NAND at comparable or higher layer counts is grown as a single continuous stack on one wafer. When a cross-section of this YMTC die is prepared for electron microscopy, the cell array does not resolve as one unbroken column. There is a boundary running horizontally through the structure, and that boundary is the next cut. Teardown analysis identifies the YMTC die as a bonded structure consisting of two wafers, an upper wafer carrying the memory cell array, and a lower wafer carrying the peripheral logic circuits that manage those cells, the page buffers, decoders, sense amplifiers, and the control logic that coordinates every read and write operation. YMTC's published technical documentation describes this two-wafer architecture as Xtacking. The split between array and logic is confirmed by the distinct process signatures visible in the material layers of each wafer when examined under electron microscopy. Conventional three-dimensional NAND places the logic circuitry at the base of the same wafer on which the memory cells are grown. This arrangement creates a process conflict that has defined much of the engineering difficulty in the field. The logic requires tight transistor geometries and precise doping profiles to operate at speed and low power. The cell array requires high-temperature oxide deposition processes to build the vertical structure, processes that would damage fine logic transistors if those transistors shared a substrate with the array during fabrication. The industry workaround has been to place logic beneath the cell array and shield it through careful thermal management, but this constrains both the logic density and the cell array process because each must accommodate the other's requirements on the same piece of silicon. YMTC's approach manufactures each wafer independently under its own optimized process conditions, then joins them after both are complete. This is the architectural fork in the road. Each wafer can be pushed as hard as its own process allows, because it never has to coexist on a substrate with something that needs different conditions. The two-wafer structure visible in the cross-section is framed in YMTC's own documentation as a deliberate design choice. But the timing carries weight. The company developed and patented Xtacking during the same window in which access to the most advanced lithography equipment was being progressively restricted for Chinese semiconductor manufacturers. Whether that restriction was the cause of the architectural direction or merely the context in which an independent engineering decision was made is something the teardown cannot settle from physical evidence alone. What the physical evidence does show is that the solution they built happens to sidestep the dependency that the restriction was designed to make most painful. The logic wafer in the Xtacking architecture can, in principle, be fabricated on a more advanced process node than the cell array wafer since the two are manufactured separately. YMTC's technical materials indicate the logic wafer uses a more refined process than the cell array, which is consistent with the design intent. The specific process node for the logic wafer in the 270-layer generation has not been independently confirmed by published teardown sources available through mid-2025, so the precise figure is not stated here. The cell array in three-dimensional NAND does not require the most advanced lithography resolution available in the industry. The vertical dimension of the stack is built by deposition, layers of oxide and nitride deposited one on top of another, not by the lateral resolution of a lithography scanner. Advanced lithography matters for the horizontal features, and the horizontal features in a vertical cell array are relatively forgiving compared to what leading-edge logic demands. The logic circuits, by contrast, benefit directly from finer transistor geometries, because smaller logic means faster operation and lower power consumption per bit accessed. By separating the two wafers, YMTC can source logic fabrication from whichever process node is available to it, independently of whatever process the cell array requires. This modularity has a supply chain consequence that is not printed on the spec sheet. Even if access to advanced lithography for large cell array wafers is constrained, the logic wafer is a small die relative to the memory array. To give that a physical reference, the logic wafer in a configuration like this is roughly the footprint of a few grains of rice set side by side, compact enough that even moderate volume production on a capable but less constrained process node can supply the logic for a large number of finished chips. The dependency on any single advanced lithography node for the most area-intensive part of the chip, the cell array, is reduced. The area-intensive wafer has more relaxed lithography requirements. The lithography-sensitive wafer is small. That geometry was not forced on YMTC by the restriction, but it fits the restriction's contours precisely. The two wafers are joined face-to-face using hybrid bonding, a process in which copper pads on the surface of each wafer are brought into direct contact and bonded without solder, adhesive, or intermediate wire connections of any kind. The electrical connections between the memory array and the logic circuits pass through this interface. Every signal that controls the cells and every data bit that moves in or out of them crosses this seam. A through silicon via, which is the conventional method for connecting stacked dies, requires a relatively large copper pillar drilled through the body of the wafer. Imagine pressing a bolt through a stack of paper to connect the top sheet to the bottom one. The bolt takes up space, adds electrical resistance along its length, and limits how many connections you can fit in a given area because each bolt needs clearance around it. Hybrid bonding eliminates that intermediary entirely, and instead presses the two wafers face to face so that their copper pads contact each other directly, pad to pad, across the entire bonded surface at once. The connection pitch drops from something visible under a basic optical microscope to something that requires electron microscopy to resolve. That shift in density is why the logic circuits can communicate with the memory array fast enough for the finished chip to deliver commercially useful throughput. YMTC's published patent portfolio in hybrid bonding is reported at 119 patents. Samsung and SK Hynix together are reported to hold 94 hybrid bonding patents. These are reported figures from patent analysis citing YMTC's own filings and commercial patent databases, flagged here as company reported and analyst counted rather than independently audited. What the patent count does not state out loud is its implication. A company that was supposed to be held at a technological ceiling by external pressure has accumulated more documented intellectual positions in this specific bonding technique than the two largest incumbent NAND producers combined. The seam is where this chip's claimed performance lives or fails. Every read and write operation crosses this interface. A defect in the bonding, a void, a misaligned pad, a contamination particle at the bonding surface, degrades or disables the connection at that location across every chip that carries it. The yield of the finished device is therefore a function of bonding quality maintained across tens of millions of pad pairs on every single die. The patent concentration is one record of how much engineering effort went into solving that problem. What the patents cannot confirm is whether the manufacturing yield at this interface and volume production at the cost targets that make the chip commercially viable actually meets those targets. That answer requires shipment volumes and cost per gigabyte data that are not publicly available at the resolution the question demands. The Xtacking architecture was publicly introduced by YMTC in 2018, during a period when the company was scaling its three-dimensional NAND ambitions and before the most severe equipment export restrictions were imposed. The architecture's development and the escalating restrictions on YMTC's access to advanced lithography tools and other critical equipment occurred in overlapping timeframes. The 270-layer generation entered mass production by the company's own public statements in a window when those restrictions were actively in place. Monolithic stacking, as practiced by Samsung and the established Western producers, scales by growing the vertical structure taller on one substrate. This approach concentrates the full process complexity in a single wafer and makes the finished chip's performance and yield both dependent on how well that one wafer's process is controlled end-to-end. It is an approach that rewards deep accumulated experience on a specific process platform, and the incumbents have that experience measured in decades. Xtacking distributes the complexity across two separately optimized wafers and concentrates the yield risk at the bonding interface, a different risk surface, one that YMTC has chosen to address through a patent-dense proprietary bonding process rather than through the lithography tools that would have let it compete on the monolithic path directly. The architecture of this chip is a direct material record of its competitive environment. The bonding seam is not only an engineering feature, it is the visible signature of a company that could not compete on the dominant industry path and built a different path instead. The two-wafer structure exists because it routes around the dependency that the restriction was designed to enforce. The 119 hybrid bonding patents exist because the company that built this path has more documented claims on the method than the incumbents who did not need to invent it. The constraint produced the specialization. The specialization produced the patent position, and the patent position is now an asset that persists regardless of whether the original restriction persists, because the intellectual property is held and documented independently of whatever policy environment surrounds it. 3 things the dissection cannot settle should be stated plainly before any conclusion is drawn from it. The teardown identifies the architecture and the bonding method, but it cannot confirm the manufacturing yield of the bonding interface at volume production scale. If the hybrid bond yield and volume is materially lower than what monolithic stack producers achieve on their mature processes, the cost per gigabyte of finished product will reflect that gap, and no public data source resolves this with the specificity needed to answer the question. The patent count, 119 for YMTC against 94 combined for Samsung and SK Hynix, comes from analyst review of published patent filings, and patent counts measure documented claims, not deployed capabilities. A patent portfolio in hybrid bonding does not confirm that every claimed method works at production yield, that the claims will survive challenge in international jurisdictions, or that the portfolio covers the specific process steps used in volume manufacturing. And the physical architecture of Xtacking sidesteps the dependency on a single advanced lithography scanner for the cell array wafer. But it does not eliminate equipment dependencies, it redistributes them. The bonding tools required to align and join two wafers face-to-face at the required pad pitch are precision instruments with their own supply chains and their own export control exposure. Whether those tools are available to YMTC at the required specification through domestic or accessible sources is not settled by examining the finished chip. What the dissection establishes is the architecture and its internal logic. What it cannot settle is whether that architecture, at scale and at cost, represents a viable long-term competitive position or a sophisticated holding pattern, and the answer to that question will be written in shipment volumes and cost structures that are not yet publicly resolved. This chip, taken apart cut by cut, shows one consistent thing across every layer. The structure is a response to conditions outside the lab. The package is standard because compatibility was a market requirement, not because the engineering team had no other option. The two-wafer split is the solution to a process conflict that also happens to root around a supply chain constraint, and the fact that it does both simultaneously is what makes the architecture interesting beyond its layer count. The hybrid bonding interface is where that solution is most technically demanding and most patent dense, and the patent density is itself a record of how much engineering effort went into solving a problem that the dominant players never had to solve because their path did not require it. The chip is not a copy of the Western approach with a different label applied. It is a different answer to the same question about how to keep scaling memory density, shaped by a different set of pressures and built under conditions that made the standard answer unavailable. Whether that answer proves durable in the market is not written in the silicon. But the fact that the answer exists in mass production with this internal geometry at this layer count is written there precisely and legibly in the cross-section of every die. The seam between two wafers is where an embargo becomes an architecture. What should we open next? The bonding tool that makes joints like this without a single drop of solder, pressing two wafers face-to-face across millions of copper pads simultaneously, or the controller chip that sits beside this die in a finished drive and decides how fast those 270 layers can actually be read? If the cut-by-cut format is how you want to follow this technology, subscribe and turn on notifications. The next dissection is already on the table.